with all the preparations done, in the case of affine schemes, we can now define schemes, the central topic of this chapter. And the idea for the definition is to mimic again what we have seen for varieties and pre-varieties. So there, a pre-variety defined as being a ringed space which has a finite open cover by affine varieties. And very similarly, now we say a scheme is a locally ringed space that has an open cover by affine schemes. So note, we have no finiteness assumption here. I'm going to comment in a second. So these are kind of the objects, and then the morphisms of schemes, we just say these are morphisms of locally ringed spaces as we introduced them before, and as we already applied it to the case of affine schemes. So the first remark is there's no finiteness assumption here. So on the one hand, we don't necessarily have a finite open cover. We can have arbitrary open covers. And also, we don't restrict any of the rings which can appear here. So both of these lead to the fact that schemes and also affine schemes are not necessarily Noetherian. So we can have infinite descending chains of closed subsets. In particular, for example, you could just take a single copy of spec K, for K a field. This spec K, this always has a unique prime ideal, the zero ideal. So as a topological space, it's just a point. And then you can get a scheme by just taking an infinite union of such points. And clearly, this is not Noetherian. You can have infinite descending chains of closed subsets. And so this is one thing which goes out of the window as we start talking about schemes. Then about the terminology. So in the previous context, we started with the pre-varieties, as here, and then we went to varieties by imposing this additional condition that diagonal is closed, so some separatedness condition. Similarly, we could now define what we have here as being a pre-scheme and then say scheme has additional separatedness. And if you look at some old texts, this is terminology there. However, the modern usage is to just call these things here a scheme. And then if you have this extra condition of diagonal being closed, you say that this is a separated scheme. We're going to talk more about this, but just if you open some old books and you see the word pre-scheme, then it's basically just this definition here. Okay, so this was the definition, and in this video we're going to introduce kind of two things which we have also seen before, namely the concept of an open and a closed subscheme. So for the open, there's really just a single choice of choosing an open subset of the topological space, and this will determine a new scheme. So if U inside X is an open subset, then we claim that taking the subset with the restricted sheaf is a scheme itself. And to prove this, well, since X is a scheme, by definition, we find an open cover by affine schemes. And then, well, we can try to intersect this cover here with U. And then each of those things is an open subset of this affine scheme UI. And then on the affine schemes, due to our preparation, we know this, the affine schemes, the distinguished open subsets are a basis of the topology. And so each of these open subsets of UI now has a separate cover by these distinguished opens. And so somehow if we throw all these things together, then of course we get a cover of this whole U by all of these things together. And then the final ingredient is that we have seen that any distinguished open inside an affine scheme is again an affine scheme, namely the one for the localization of the original ring at this element here. And so all of these things are affine schemes, and so we have covered U by these things, and so by definition, this is the scheme itself. Here you see how all the different ingredients from the previous videos come together. And this thing is called an open subscheme of X. And here we see, I mean, specifying this is purely a topological input. So somehow you just input this open subset, and then you get a new scheme out. So for closed subschemes, it actually turns out to be a bit more complicated. So a closed subscheme we define as being a morphism from another scheme Y to X with some extra properties. It's not just that Y is a closed subset of X, and then we get a scheme structure on this, but we actually specify some extra data here. And the extra conditions that we need is that for this morphism here, there exists an open cover of X by affine schemes. Again, we take these kind of affine charts, and we want that when you restrict to this cover, so you somehow take the UI in here, and then you have the preimage of UI mapping via the restriction, then you get a map here, and you not only require that this preimage here, which is now immediately use the part A. So this preimage here is a scheme that we know because it's an open subset of Y. And we want this not just any scheme, but in fact it is an affine scheme. And this restricted map here puts this affine scheme here as an affine subscheme of UI. So in other words, if you look at this map of affine schemes, you look at the map of rings in the other direction, then this map of rings should be a surjection. That is the condition. And we have already seen with the affine subschemes that it's not just enough to specify what the image here is, but it's actually necessary to specify this full map. So here is also this picture. You have X, and then you have this map from Y to X, and then you want that on this affine open cover, this restricted map here puts this little part here as a closed subscheme of this affine scheme. And two remarks maybe. The first is that that this implies that this map here is as a closed image, because you can check the closedness of this image on this open cover, and we have seen that for affine subschemes, the image is closed. And also, this thing here is an isomorphism on the level of topological space, a homeomorphism onto its image. Again, this is something which you can check on an open cover of target. So on the purely topological level, this is the inclusion of a closed subset in here, but then you have extra data. Another statement here, which we are going to see in different variations in the following, is that the condition that we impose here is that there exists an open cover by affine schemes having this property. In fact, it's also true that for any open cover of X by affine schemes, this condition is still satisfied. So for many, but not all properties of morphisms and schemes and so on, it's true that there's a kind of equivalence between there exists an affine cover with this property, and for all affine covers, this property holds. This is one example. So just to keep in mind. Okay, so this was the basic definition of schemes, and then for the rest of the chapter, we're going to explore this a bit more and also see now, is the entire first part of the lecture kind of separate, or can we import this into this language of schemes and then see all these pre-varieties which we had as examples of schemes? Okay, so that's the next topic.